All right. Hello. Let's go over the solution to problem 2.1 from this week's worksheet, week 4. So in this problem, consider all polynomials to be over GFP or mod P, where P is greater than n for all the n defined in the problems. So let's just first review the properties of polynomials. So property 1, a non-zero polynomial of degree d has at most d roots, and then given d plus 1 pairs, on the polynomial, pairs of points, with all the xi distinct, then there is a unique polynomial p of x of degree at most d such that p of xi is equal to yi for I in this range. So kind of another way to say that is just d plus 1 points uniquely determine p of x, right? D plus 1 points on the polynomial, which with each x coordinate distinct. Okay, so yeah, let's just start with 1a. So how many distinct degree n polynomials? Sorry, how many distinct degree n polynomials are there? So recall that the form of the polynomial is so let's just call it q of x. So q of x has the form um a to the n, x to the n, plus a sub n minus 1, x to the n minus 1, all the way to a sub 0, right? And again, this follows from the fact that this is a degree n polynomial, so then there must be um, n plus 1 terms in this series because the last term doesn't have a like an x in it, so it's x to the 0 essentially. So there are n plus 1 terms, and the polynomial is degree n. Okay, so to solve this question, I claim that a polynomial is also uniquely determined by its coefficients. So so probability 2 says that a polynomial is determined by like the d plus 1 points that lie on it, but I'm also going to claim that its n plus 1 coefficients here in this expansion for q of x also uniquely determine q of x. So that just follows from the fact that if you take d plus 1 points on a polynomial, then I can write like q of 1 is equal to a to the a sub n times 1 to the n plus a sub n minus 2 times 1 to the n minus 1, and so on to a sub 0. And then I can also plug in q sub 2, or and then I get another like I get another expression when I plug in x equals 2. I get another y value out for q of x, right? So I just chose arbitrary values like for x equals 1, x equals 2 here. It doesn't matter what these points are as long as they lie on the polynomial, right? But what I'm trying to show is that when you have d plus 1 points on this polynomial, or in this case, n plus 1 points, right? Because I'm using n as our exponent, um, I'm trying to show that we get we get n plus 1 equations. That's what I'm getting at. And again, why are there n plus 1 equations? It's because we're saying that there are n plus 1 points on this polynomial that uniquely define q of x. Okay. So if you imagine just like going down this list, like with n plus 1 points, then I will get n plus 1 equations. Okay. And note that we're trying to solve like my again, my claim is that the coefficients uniquely determine the polynomial q of x, right? So if I have n plus 1 equations like related to q of x where I plug in a point, and there are also n plus 1 coefficients in this polynomial, then I should be able to solve for every coefficient, given that I write down all n plus 1 equations, right? Because you have a system of n plus 1 equations with n plus 1 unknowns. So it's exactly the case that you should be able, you can, like if you were to go through the long process of writing everything out, you should be able to solve for all the coefficients of the polynomial. Now, obviously, that isn't the best way to do it because, we learned like polynomial interpolation, right? Or Lagrange interpolation. That's unrelated, but I'm just trying to illustrate that we can solve for all the coefficients given n+1 equations. Okay. So given that that the polynomials are uniquely determined by by um by these n+1 coefficients, then basically the idea is we want to pick different values for the coefficients to get different polynomials, right? So we call that we're working under mod p or GFP. So I mean, let's just think about it. So let's start from the end. So a sub 0, right? Because we're working under mod p, each coefficient um, can, or every coefficient except for one of them. I'll get to that in a second. But basically, almost every coefficient in this expansion can take up to p values, right? Because we call that in mod p, um, like every value takes up or lies in this like set from 0 to p-1, just by definition. So that means a0 can like take on p like different values, right? And so we basically repeat that logic for all these coefficients. But the key thing is to note that for this one is different, okay? Because the question is asking how many distinct degree n polynomials are there? So we're imposing this restriction that q of x must necessarily have degree n. So that means this coefficient it's non-zero, like it can't be equal to 0. Okay. Because we need q of x to be of degree n. And if a sub n were 0, then this term wouldn't be here, right? So you wouldn't have an x to the n term, and therefore q of x would not be a degree n polynomial. So actually, because a sub n cannot take on the value 0, there are actually p-1 values for a sub n, right? So in this case, it would be able to take up or take on like the values of 1 through p-1, but not this value 0, right? Okay, so given that this is the case, we can basically use counting principles to find the total number of polynomials. So what does this look like, right? So we have p-1 possibilities for a sub n, and we multiply that by p possibilities for a sub n-1, right? Because a sub n-1 can be 0, because we still have, like, it doesn't matter what this coefficient is, just because, like, as long as we have a sub n being non-zero, then we do indeed have a degree n polynomial, right? So p-1 times p for the n x to the n-1 term. Then we have p for x to the n-2. And we just keep going, right? So in total, right? Because again, like I said, in this expansion for q of x, we have n plus one terms, right? But I claim again that the first term, there must only be p-1 possibilities for the coefficient. That means in total, we have p-1 times p, where this p is multiplied n times, right? It's not n+1, because again, just to restate, the first term has only p-1 possibilities. So this is p-1 times p to the n. That's our final answer. Okay. And I just like I claim that the polynomial was uniquely determined by its coefficient just because like it makes things easier to analyze, right? All we have to do is just look at the coefficients and be like, hey, there are this many possibilities for this coefficient, and then this one, and then so on. And we use counting to determine the number of total polynomials, right? But I mean, you could have also equivalently said that like just because like there are d+1 points that uniquely determine the polynomial, that like all of those points must also lie in like there must be uh p minus one, like p values for each of those points, right? But then you would claim that like, okay, one of those points has to lie on like one of those points like can't be like there's some restriction on one of those points basically. Like basically this argument with coefficients is equivalent to the argument with points. They're the same thing because since I said d plus one points determine a polynomial, then that means I just said that like d plus one coefficients, the d plus one coefficients in the polynomial also uniquely determine it. So it's like they're kind of, since they're like the same number, it doesn't really matter how you look at it. It's just that the coefficients are easier to consider just because we know the explicit expansion for q of x just by definition of a polynomial. Okay. Okay. So part B is actually easier. Um, so we're just gonna use our result from part A, right? But what's the difference here? The difference here is that um, now the problem is saying that p of x. Okay, I use q of x here, but like whatever. It's saying that q of x must be um, of degree at most n, right? At most n. So that means we don't need the constraint that a sub n has to be non-zero, right? Because um, like if a sub n is zero here, then it's totally fine because that means our like the problem is saying like the polynomial must be of degree at most n. So we don't need the leading term to be something times x to the n. It can be like whatever we want. So the only difference here is that um, we have p multiplied by itself n times. Or sorry, p multiplied by itself n plus one times, right? And that's because again there are n plus one terms in the expansion for q of x, and each coefficient has p possibilities for it. So this is just p to the n plus one. Okay. And I also want to point out something that in this problem, it explicitly says p is greater than n. So like you might take that for granted, but like I just want to point out that like this is important, right? Because if this were not the case, then like you basically wouldn't be able to write out these n plus one different um n plus one different terms in this expansion for q of x, right? And why is that the case? It's because like suppose p was equal to n, right? But then that means x to the n, like x to the n would be congruent to x to the zero, right? Because under mod p, if p is equal to n, then n must be congruent to zero mod p. If that makes sense, right? So actually, like, it's very important that we have this constraint that p is greater than n, because otherwise, like, if it was equal to n, or if p was greater than n, or sorry, if p was less than n, then like we wouldn't be able to write out these n plus one different terms in the polynomial. Okay. Yeah, just an aside, but yeah. So okay, so part C. So how many distinct polynomials of degree d at most n? Again, at most n, not of degree n. Are there such that p of 0 equals 1 and p of 1 equals 2? Okay. So so going back to the argument with the like how we were plugging in points into these n plus 1 equations, right? Because in this problem, like this problem says that it's giving us two of the points on the polynomial. So that means these points are not like free for us to choose. Okay. So that means in like if you go back to solving like uh like the systems of equations, then like you don't have any more freedom to like pick the points on the polynomial, or sorry, you don't have as much freedom to pick the points on the polynomials, right? Because I'm telling you that like I'm giving you two of the points on the polynomials already. So you can't change those. So that means what does that mean, right? That means so so property two of the property two of polynomials claim that d plus one points determine p of x, right? Um so I'm trying to write this out. So again, n plus one points um uniquely determine p of x, right? So but again, like because I've given you two of the points on the polynomial already, that means we're only free to pick n minus one, n minus one points on the polynomial, right? So by the logic from before, like I claim that the d plus one or I'm using d and n interchangeably, but like the d plus one points on the polynomial is like it's equivalent to saying that um like if d plus one points on the polynomial uniquely determinate, then its d plus one coefficients also uniquely determinate, right? So if I'm telling you that there are n minus one points left that we're free to pick, like we're free to do whatever we want with, then there should also be um like we can only adjust like n minus one coefficients as well, right? Because if you imagine us solving the systems of equations, because I've told you that p of zero is equal to one, p of one is equal to two, that basically is equivalent to saying that like I've already told you what two of the coefficients, what two of the coefficients in our polynomial are. Okay. So given that like two of these coefficients in the polynomial are already fixed, then what does that mean, right? That means there's only one possibility for one of them. There's one possibility for another of them, but for the rest of them, we still have our normal p choices. Okay. So again, since there are n plus n plus one terms with two of them being one, that just means that our total number of possibilities is p to the n minus one. Okay. Again, just because two of the points are fixed. So we essentially just have less freedom for what our polynomial can be. And again, note that this says degree at most ends, so we don't have to worry about the weird case, not weird, but like the part A case where a sub n must be not zero, right? We're just free to multiply p however many times we want. So we have p to the n minus one. Okay. So yeah, that does it for problem 2.1. If you have any questions, I encourage you to reach out to your mentor. Um, but yeah, hope you guys have a good day.